Hello everyone. In this video I'm working on a section titled Modeling with Systems of First Order Differential Equations. And in this video I'm going to go over just a couple examples of mixture problems where you have a few tanks and water, some sort of mixture of water and salt. We're just working with salt here as being pumped in and pumped out of these tanks, and we're asked to set up a model, set up a system of differential equations describing the amount of salt in these tanks at any given time, and not actually solve the systems, right? So in future videos we'll go into how to solve systems of first order differential equations. But for right now we are just asked to set up the system. Okay. So in the textbook I'm looking at the first problem. Well, I've drawn it out here, but let me read off to you what it says. So it's use the information given in the figure 3.3.6 in this book is that picture I just drew that I have drawn to construct a mathematical model for the number of pounds of salt x1 of t, x2 of t, and x3 of t at time t in tanks A, B, and C respectively. Now, this is the figure that's being talked about here, way up top, 336. Okay, so I'll describe the picture here. So we have these three tanks, A, B, and C. They each have 100 gallons of liquid in them. Tank A, you have 4 gallons a minute of pure water being pumped into tank A at 4 gallons per minute. Also being pumped into tank A, see that follow the arrows. You have this mixture from tank B being pumped into tank A at 2 gallons a minute. And then being pumped out of tank A is the mixture from tank A, and that's being pumped out at 6 gallons per minute, which is then being pumped in to tank B at the same rate, at 6 gallons per minute. So tank B, you have this mixture from tank A being pumped in to tank B at 6 gallons per minute. You also have the mixture from tank C being pumped into tank B at 1 gallon per minute up here. Then you have the mixture from tank B being pumped into tank C at 5 gallons per minute, and that's being pumped out of tank B and into tank C. Alright, and then in tank C you have the mixture being pumped out at 1 gallon per minute, this mixture being pumped in at 5 gallons per minute, and the final mixture in tank C here being pumped out at 4 gallons per minute. So a lot going on here, 3-tank problem. And we're asked to set up a system of equations involving the amount of salt in each of these tanks at any given time. All right, so I have a very rough sketch of that diagram here, with all the rates at which liquid's being pumped in and out of each tank. All right, so x1 of t again is the amount of salt in pounds in tank A at time t, and that's in minutes. Right. X2 of t is the amount of salt in pounds in the tank B at time t, and x3 of t, this function is representing the amount of salt in pounds in tank C at time t. Alright, so these, we're just going to work one tank at a time. And I've put up a video on these mixing tank problems before where we just work with one tank and talked about the amount of salt in one tank. Basically going to do the same thing, but just one tank at a time. Okay. So for tank A, we're going to talk about the rate at which the amount of salt in tank A, so that's x sub 1, the rate at which that changes over time. Right, so dx1 dt. And as you've seen in previous videos of mine, if you've been watching, this is going to be equal to the rate at which salt is coming into the tank minus the rate at which salt is coming out of the tank. So R in minus R out. And all the units on these should be in pounds per minute, right? Because the numerator is a change in the amount of salt, which would be in pounds. Denominators are change in time, which would be in minutes. So all these rates I'm finding should be in pounds per minute. All right. So first, the rate at which salt is coming into tank A. Well, you actually have two liquids being pumped into tank A. Now, pure water has no salt at all. So 0 pounds per minute from the pure water. No salt at all coming into there. Plus, though, right, on top of that, we have this mixture from tank B being pumped into tank A at 2 gallons per minute. Right, but I want to convert this to how many pounds of salt is that per minute. So I'm going to multiply by what's the concentration of the salt in this tank B mixture. So how many pounds per gallon? Well, at any given time there are x2. Right, remember x2 is the amount in tank B. There are x2 pounds in tank B per the 100 gallons that are in tank B. Right. And in every single one of these, the amount of liquid's always going to be 100 gallons. Because you see here, I got 6 coming in, 6 going out for tank A. You've got 7 going in, 7 going out per minute, 7 gallons going out per minute in tank B. And tank C, you have 5 coming in and 5 gallons going out every minute. So every single one of these tanks is always going to have 100 gallons of liquid in it. Not increasing, not decreasing. So it's x2 pounds per 100 gallons. That's the concentration of salt in tank B's liquid, and 2 gallons of that per minute are coming into tank A, and then the gallons cancel. So I'm left here with 2 pounds per 100 minutes, or 2x2 over 100, or just x2 over 50 pounds per minute. All right, so that's the rate at which the salt is coming into tank A, x2 over 50. All right, then the rate at which it's leaving the tank, right, R out. Look at the arrows coming out of it. Well, there's only one arrow coming out of tank A, and it's coming out from tank. So I need to know what concentration of salt is there in tank A. It's coming out at a rate of 6 gallons per minute, but I'm going to multiply that by the concentration of salt. How many pounds per gallon? Well, in tank A there are x1 pounds, right, at any given moment, divided by the 100 gallons, right, and then your gallons will cancel. So this is 6x1 over 100, but if you were to reduce this, this would be 3x1 over 50 pounds per minute of salt coming out of tank A. So the first equation in my system is dx1 dt equals x2 over 50 minus 3x1 over 50. All right, so that's tank A. Second equation will relate to tank B. So again, the setup will be dx2, right, because the amount of salt at any moment in tank B is labeled x2. dx2 dt, again, will be the rate at which salt is going into the tank minus the rate at which salt is going out of the tank. All right, so the rate at which salt is going into the tank, into tank B, well, there are two arrows, going into tank B. This first arrow is from the mixture from tank A. So it's going in at 6 gallons per minute, multiplied by the concentration of tank A, which was x1 divided by 100, right, pounds per gallon. Right, but on top of that, right, not only is that coming in, but also this mixture from tank C is pumping into tank B at 1 gallon per minute. And I need to multiply that then by the concentration of salt in tank C. So that's x3 pounds of salt. Remember, the amount of salt in tank C at any time is x3 divided by its 100 gallons. Right, so gallons are canceling there. And so the rate at which salt is coming in, if I reduce these, is 3x1 over 50 plus x3 over 100 pounds per minute. Okay, now that's just the rate at which the salt is coming in. Now I look at the rate at which the salt is going out of tank B. Right, now look at tank B. There are 2 arrows coming out. So you have one where there's 2 gallons a minute coming out, and then multiply by the concentration of salt from tank B, which would be x2 over 100. Right, there's x2 pounds of salt at any given time, and there's 100 gallons of liquid in the tank B at any given time. And on top of that, what else is coming out is this 5 gallons per minute of the tank B mixture, and times the same concentration, x2 over 100 pounds per gallon. So we have 2x2 plus 5x2, so that'd be a total of 7x2 over 100. They both have a denominator of 100 here. 7x2 pounds per minute of salt leaving tank 2. Right? So minus 7x2 over 100. Right? That's the rate out. And there we have it for tank B. And now we'll move on to the third equation in the system, tank C, and then I'll just write it all together. All right. So for tank C, a new piece of paper. Same thing, right? We're going to talk about the rate at which the amount of salt in tank C changes over time. So that's dx3 dt. And same as with the other 2 tanks, that's the rate at which the salt enters the tank minus the rate at which the salt exits the tank. Alright, so the rate at which the salt enters tank C, now there's only one arrow that goes into tank C, and it's from this tank B solution. And that's coming in at 5 gallons per minute. And we multiply by the concentration of salt in that mixture, which would be x2, right, the amount in tank B, x2 pounds of salt at any given time divided by the 100 gallons that are in tank B at any given time. The gallons cancel, and 5 over 100. This is just x2 over 20 pounds per minute. That's the rate at which the salt is entering tank C. So x2 over 20. And then the rate at which it's leaving the tank, well, there are 2 arrows coming out of the tank, and both with that tank C mixture, so they'll have the same concentration. So I got the one up here with the 1 gallon per minute times the concentration, which would be x3 over 100. Right, there are x3 pounds of salt per the 100 gallons that are always in tank C, and then gallons would cancel. But on top of that, right, plus this other arrow coming out, at a rate of 4 gallons per minute, and the concentration's the same. It's x3 pounds over the 100 gallons in tank C. And putting those together, you have x3 plus 4x3, that's 5x3 over 100, which would just be x3 over 20, right? 5x3 over 100 be x3 over 20 pounds of salt per minute coming out. So minus x3 over 100, and sorry, x3 over 20. I just said that, right? X3 over 20. So then putting all these together gives us our system of first order differential equations. All right, so the system in question here, you have, the dx1 dt was equal to what? I had this, right? It was, I'll line them up too. Make it, so it'd be negative 3/50 times x1 plus 1/50 times x2. All right. Then my second equation from tank B is this here. dx2 dt, putting positive 3/50 times x1 minus 7/100 times x2 plus 1/100 times x3. And then finally my equation here for the third tank, dx3 dt, the rate at which salt is leaving tank C, is changing in tank C, is no x1 and then 1/20 x2 minus 1/20 x3, right? And there's the final result, right? And that's all we're asked to do. All right. In a later video, later section, I will go over how we would go about solving such a system. But for right now, all we are asked to do is set up a system of first order differential equations like this. Okay. And if we were to solve such a system, right, our solution to this system would be a function x1 and a function x2 and a function x3 that give me the amount of salt in tank A, B, and C respectively at any given time. All right, but again, we're not doing that right now, just yet. All right, so hopefully all that made sense. Then I just wanted to go over one more problem that might be a little more involved, but we'll see what you think of it. And it involves this drawing. All right, it's only a 2-tank problem. But notice in this 2-tank problem here, nothing's being introduced from the outside and nothing's exiting the system of tanks. The water is just, the liquid, the solution is just flowing around and around between these 2 tanks. It is what they would call a closed system. All right, so that previous example would be an open system, because things are going outside the system of tanks. So here's a closed system of tanks with this water flow, this mixture flow. And again, we're talking about salt. Now this is actually coming from this question here. Okay, so two very large tanks, A and B, are each partially filled with 100 gallons of brine. Right? Now remember, brine is a mixture of salt and water. So like this, right? This is the drawing I had. Right. Now it does say they're very large tanks, so let's assume that they both can hold much more than 100 gallons. But to start with, they have 100 gallons of brine. Initially, 100 pounds of salt is dissolved in tank A, and 50 pounds of salt is dissolved in tank B. The system is closed in that the well-stirred liquid is pumped only between the 2 tanks. All right, so again, back to my drawing here. So, just as before, let's say x1 of t is the amount of salt in pounds, right? The number of pounds of salt in tank A at time t, where this is time is in minutes, it looks like. Right? And from what we've just been told, we have an initial condition. We're told that initially 100 pounds of salt is dissolved in tank A. So x1 of 0 is 100 pounds. Or just x1 of 0 is 100. So 100 gallons of liquid, and in that liquid 100 pounds of salt to start with. And then we have another function, say x2 of t, is again the amount of salt in tank B, right, at time t. And we're told that x2 of 0, the initial amount of salt, is 50 pounds. All right. So to start with, there's 100 pounds of salt in this tank to start with. And there are 50 pounds of salt to start with initially, right, in tank B. And then the mixture's flowing in this closed system. Now you may notice something. The mixture from tank B is flowing into tank A at a rate of 3 gallons per minute, whereas the mixture from tank A is only flowing out into tank B at 2 gallons per minute. So that means as time goes by, the amount of liquid in tank A will increase. Right, the liquid in tank A will increase by a gallon a minute, right? Because 3 gallons are coming in every minute, 2 gallons are going out. That's a net increase of 1 gallon. And the opposite will happen over here in tank B. If 3 gallons are leaving tank B every minute and 2 gallons are coming in, that means more is leaving than is coming in. So the amount of liquid, the amount of brine, the mixture in tank B, will decrease, and we'll talk about what that means when we set up our equations. Right. Okay. So as before, we can start with setting up a system. Now I'm not going to write the R in, R out this time. I'll just write what they are. Right. So let's talk about tank A and the change of the amount of salt in tank A over time. So again, same setup as the other tanks, the other tank mixture problems. So the rate at which the amount of salt in tank A changes with time, the dx1 dt, is the rate at which it's coming in. All right. Now the rate at which it's coming in, maybe I will write it. All right. So the rate at which is coming in, R in, well, it's coming in at 3 gallons per minute. All right, 3 gallons per minute. And then, just as before, I'm going to multiply this by the concentration of that liquid, the concentration of salt. Now that liquid that's coming in is coming from the mixture from tank B. Now the amount of salt at any given time in tank B is x2. Right? There are x2 pounds of salt at any given moment, divided by now the number of gallons in tank B. The number of gallons of that mixture in tank B at any given moment is not always 100. Because like I said, the amount of liquid will decrease over time. Let's think about it. If there's 100 gallons in the beginning, a minute later, there'll be 99. Right? Because 3 will leave, 2 will enter, you'll have 99 gallons. Then another minute, you'll have 98. So basically, there's a net loss of 1 gallon every minute. So after t minutes, right, so this is at time t, there would be 100 minus t gallons in tank B. And so the concentration of the mixture in tank B, the concentration of salt, would be x2 pounds of salt divided by the 100 minus t gallons at that moment. Hopefully that makes sense. So that's the rate at which salt is entering tank A. So that'd be 3x2 divided by the quantity 100 minus t pounds per minute. All right, now the rate at which salt is leaving tank A are out. Well, there's only one arrow coming out, right? It's leaving at a rate of 2 gallons per minute. Right, and then that salt mixture, right, that's the mixture from A. Oh, so what's the concentration of salt from A? Well, there are x1 pounds of salt in A at any given time. And the number of gallons of mixture, the number of gallons of liquid in tank A at any given time would be 100 plus T, right? Because there's a gallon being gained every minute, right? 3 gallons are coming in, 2 gallons are going out. So that'll be 100 plus T gallons, okay? So the rate at which salt is exiting tank A would be 2x1 divided by 100 plus T pounds of salt per minute. And we subtract these, right? So dx1 dt would be 3x2 over 100 minus t minus the rate at which it's going out, 2x1 divided by 100 plus t. All right. All right. And then very similar, we look at tank B, talk about dx2 dt. And then really these just kind of switch, because if you look at tank B, the rate at which salt is coming in, it's coming at the 2 gallons per minute, and then multiplied by the concentration of tank A. Well, that was this here. That was this 2x1 over 100 plus t. Minus the rate at which it's going out is this 3 gallons per minute times the concentration of B. Well, we already did that. That was the 3x2 divided by 100 minus t. Okay. So again, hopefully all that made sense. So there's your system of first order differential equations for this closed system here. Right. And we're not going to be going into solving this system, well, just yet. I mean, I guess we could, because there is actually a second part to this that I'm going to get into. But in the course I'm teaching, if I were to question you, so far, all I would want you to do is be able to set up this system at least. All right, so let's look at the second part of this question. All right. So they're saying here, find a relationship between variables x1 of t and x2 of t that holds, that is always true at any time t. And then use this relationship to help find the amount of salt in tank B at 30 minutes. All right. So they're talking about, is there some sort of relationship that holds all the time? Let's think about that. Remember, x1 of t represents the amount of salt in tank A at any given time, and the initial amount is 100 pounds of salt in tank A, and x2 of t is the amount of salt in tank B at any given time, and that initial amount is 50. Well, being that it is a closed system, no liquid's being introduced, no liquid is leaving. You have the same amount of liquid in these two tanks all the time, right, in this entire system. Well, if that's the case, the amount of salt never changes. So you see how I start off with 150 pounds of salt. So no matter how much time passes, I mean, the salt's just getting tossed around, there's still always going to be 150 pounds of salt. So here's a nice relationship between x1 and x2 that is always true in this closed system. X1 of t, right, the amount of salt in tank A, plus x2 of t, the amount of salt in tank B, is always going to be 150 pounds. That's always true in this particular example. All right, and then we can actually use this relationship to help us solve for x2. The question was, use this relationship to help find the amount of salt in tank B, right? So x2 at 30 minutes. So if I solve this for x1, see how x1 would just be equal to 150 minus x2. And I'm going to substitute this for x1 in this equation involving the derivative of x2. All right, let's see what we get. So subbing yields the following. We have dx2 over dt, right? The derivative of x2 with respect to time is 2 times x1. So that's going to be 300 minus 2x2, right? Distributing the 2 over this, divided by 100 plus t, or t plus 100. All right, then minus 3x2 over 100 minus t. Okay. Well, this is actually now a first order linear equation in x2. And if it's a first order linear, I should be able to solve it. We also have an initial value problem here. X2 of 0 we said was 50, right? There was originally 50 pounds in tank B. 50 pounds of salt. Okay, so putting some things together, what I'm going to do is I'm going to get this in standard form for a first order linear. So bear with me here. So we have dx2 dt, just a lot of algebra right now, equals, I'd have 300 over 1, I'll do t plus 100, and then minus 2x2 over t plus 100, and then putting this minus in the denominator here, that would make this t minus 100, so plus 3x2 over t minus 100. And then I want to get these two things together. I can actually, let's just keep this the way it is, factor out the x2, get it to one side. All right, so here's the standard form. So dx2 dt plus, and then I have 2 over t plus 100 minus 3 over t minus 100 x2. Not x squared, sorry, x2. All right, all I did was add this, subtract that, factor out x2. And that's equal to 300 over t plus 100. So now we have the equation in standard form for a first order linear. And if it's in standard form, I should be able to get an integrating factor using this. Let's say I call this p of x here, this 2 over t plus 100 minus 3 over t minus 100. And I get an integrating factor. Say that's e to the integral of this p of x. So that'd be e to the, now that'd be 2 times the natural log of t plus 100 minus 3 times the natural log of the, the absolute value of t minus 100. And if I use some properties of logarithms here, this would be t plus 100 squared, t minus 100 cubed, and we divide, and so this ends up being t plus 100 squared divided by t minus 100 cubed. Then I multiply both sides by the integrating factor. So again, a lot of stuff here that hopefully you're familiar with. Hopefully you remember how to do from earlier videos or earlier sections. And then this left side would become the the derivative of this integrating factor times the variable x2, right, with respect to t equals, and then multiplying this on this side, we'd have 300 times the quantity t plus 100 divided by t minus 100 cubed. Okay, and then we'd integrate with respect to t. Alright, so this isn't very nice. I mean, it's not terrible, but I'd rather not waste a lot of time doing a bunch of integrations. So what I'm going to do is I'm going to integrate this with respect to t and come back when I'm all done, and I'll leave it to you to fill in the details. Okay, so again, I did this off on a separate piece of paper because it would take a little bit, and the video is already over half an hour. But you'd have this equals, integrating, you'd have this integrating factor times x2 equals the integral of this side, which gives you some crazy expression. Not crazy, but it'd take a little bit to do. Just go back, hopefully you remember how to integrate. Lots of methods. So integrating and solving for x2, get x2 alone. Then you'll have some constant here, and using the fact that x2 at 0 when t equals 0 is 50, the value of that constant would be negative 5 over 3,000. And you can simplify that if you want, but and we get the value of x2. x2 of t would be 300 divided by t plus 100 squared times this big quantity here, negative 5 over 3,000 times the quantity t minus 100 cubed minus t times the quantity t minus 100. And then finally, x2 at 30 minutes. All right, plugging in 30 here, and I did this with the calculator on my own earlier. This is approximately 47.4. And this was pounds of salt, right? So, given that this closed system always has 150 pounds of salt in it, after 30 minutes, there would be about almost 47.5 pounds of salt in tank 2, so it would decrease by a little bit. It started off with 50 pounds. Half an hour later, it's down about 2.6 pounds. But yeah, so that was a little more involved than I'd be expecting from most of you in this section here. Like I said earlier, what I want mostly out of this section on modeling with systems is to actually write the model, is actually write the system of equations that model that scenario, model this two tank closed system problem. All right. Okay, so again, lots of, now I know again I left a lot to you there with the integrating and algebra and whatnot, but that's not the important part. The important part is being able to set up these systems. All right, so hopefully watching me go through this, setting up these systems and these couple of examples help you when you're working on similar problems. And thank you very much for watching.